Hi, everyone. First of all, I would like to thank the organizers for putting together this conference and for giving me an opportunity to present my work here. So for those of you who do not know me, my name is Manibrata Sen. I'm a postdoc at the Max Planck Institute in Heidelberg. And the title of my talk would be Supernova Neutrinos from Home, and how can we use neutrinos from a core collapse supernova to test new physics. So the field of core collapse supernova and neutrinos from core collapse supernova has always been quite exciting and interesting. However, the main impetus to the field came from this particular event when in 1987 we observed around 30 neutrinos from a supernova in the Large Magellanic Cloud around 50 kiloparsec away or so. With only 30 events, we have been able to do incredible amount of physics. This underlines the fact that a core collapse supernova can actually be like a wonderful laboratory to test extreme values of fundamental physics. So since I do not have a lot of time, I would not go into the entire details of the mechanism of a core collapse supernova. However, I'm going to give you a little bit of a gist. So this usually happens when you have a very massive star, more than 8 solar masses or so, and these stars would have a gravitational pull towards the center because they're extremely massive, and for quite some time, they would be essentially supported by electron degeneracy pressure inside this iron core. However, a point comes when this degeneracy pressure cannot really support the gravitational pull, and this leads to a collapse. This collapse continues until the central core becomes stiff. It reaches very high nuclear densities. This resists further infall, and this leads to a shock wave. And this shock wave is what is expected to cause a successful explosion. Now, in this whole procedure, a large number of neutrinos are emitted. And these neutrinos are believed to play a very, very important role in causing a successful explosion. And it's very important for us to understand and study these neutrinos. So for a theorist, this whole problem is very complicated, and it helps to break it down into its simplest form. You have a supernova envelope. There is a central core, a neutrino sphere. This exists for about 10 or something kilometers. And inside this core, neutrinos are collisional. The surface of the neutrino sphere acts like the surface of free streaming for neutrinos. Now, as the neutrinos propagate outward, they encounter a large neutrino density. And this is what makes the entire problem of neutrino propagation in a supernova very complicated, because unlike in a sun, neutrino density in a core collapse supernova or any other compact object can be extremely large, which means that as the neutrinos propagate outward, they forward scatter with all other neutrinos in the bath through Feynman diagrams of this process. And this gives to a self-interaction potential, much like the MSW potential that some of you might have heard of, except that now this potential is with neutrinos. And what this implies is that because of this potential, neutrinos can actually be coupled to each other. And this leads to very, very interesting effects known as collective neutrino oscillations. However, I would not be talking about this in this talk, but if there are questions, I would be more than happy to answer this in the discussion session. Now, as the neutrinos propagate even further, the neutrino density goes down, and eventually what takes over is the forward scattering with the background fermions, what is also popularly known as the MSW effect. Eventually, the neutrinos go all the way through the interstellar matter, and then they eventually arrive at the Earth where we detect them. This is the entire problem. So the entire process of neutrino emission from a supernova takes place roughly over a period of 10 seconds or so. The first or 30 milliseconds or so is called the neutronization burst. This burst is very interesting because this burst is mostly dominated by a large flux of nu e's with subdominant flux of the nu e bars and the non-electron flavors, which we call as nu x. Because of this large dominance of nu e flux is a very, very good laboratory to do all sorts of new physics tests. Now, after this, as we go more into the 100 millisecond time window, the other neutrino flavors also start taking over, and then the neutrino flavor hierarchy becomes less obvious. This is the accretion phase. This is the phase when collective oscillations and these neutrino self-interactions are most dominant. So this is a phase where basically the shock wave that was launched that eventually loses energy and stalls, and then matter accretes on top of the shock wave. And eventually, these neutrinos are expected to lead to re-energize the shock wave, causing a successful explosion, which means that the shock wave goes off and neutrinos are emitted, and this leads us to the cooling phase, which goes on for almost like a period of 10 seconds or so, where basically the star cools by emitting more and more neutrinos. This part is mostly characterized by a thermal flux of neutrinos, and this cooling argument would also be sensitive to new physics, as we would see. So these neutrinos are basically our only way of probing the interiors of these very, very dense objects. Now, the main focus of the talk is the following. Suppose a core collapse supernova goes off tomorrow. Just like some of you might have heard that last year there was a core collapse supernova, although it was not very close by, but it was near the Big Dipper. But imagine tomorrow a galactic core collapse supernova goes off. With current detectors, we can detect like tens of thousands of neutrinos. What can we say about sensitivity to new physics? So new physics essentially can have two kinds of effects. One, it can directly impact the neutrino spectra or the flux that we see. So our simulations tell us what these neutrino spectra or the flux should be like, and new physics can in principle alter this. And this can be used to put constraints on new physics scenarios. Or it can impact the neutrino luminosity and the average energy. And in turn, this would also change the duration of the neutrino burst. So if you remember, I say that usually you expect the neutrino burst to go on for a period of 10 seconds or so. But if you have new physics, this duration can be limited and smaller. So, and this feature is a robust feature of all simulations. Almost all simulations see this kind of a neutronization peak. And because there is this large hierarchy of nu e's, this phase is almost not affected by collective oscillations. However, this is only true in the absence of new physics. Once you put in new physics, you can also have collective oscillations in these scenarios. And this neutronization burst phase had already been shown almost 20 years ago to be a very, very good probe of the neutrino mass ordering. Typically, within this MSW adiabatic resonant conversion paradigm, the nu E is always propagates as the heaviest state. So depending on the mass ordering, the nu E comes out either as the nu 3 in the normal mass ordering or the nu 2 in the inverted mass ordering. Now remember, the neutronization burst is mostly nu E, and you can assume that the other flavors are almost zero in this case. So if you are in the normal mass ordering, the luminosity of the nu E's that you see at the Earth is basically just given by this quantity, which is essentially 2% of the original flux. On the other hand, if you are in the inverted mass ordering, this is emitted as a nu 2 and you get almost 30% of the original luminosity. So depending on whether you see a large peak or you see a smaller peak, you can actually use this to probe the neutrino mass ordering. However, any kind of new physics scenarios that exist can actually change this whole picture. So for example, let's look at non-standard neutrino decay. So we know that within the standard model, neutrinos can decay radiatively, but neutrinos can also have non-standard decay processes where, for example, you can have a very light scalar particle and then a heavy neutrino can decay into a light neutrino and emit a scalar. Now let's take the simplest of scenarios where, for example, in the normal mass ordering, the nu 3 decays to the lightest particle, which is the nu 1. So if there is no decay, then as I said, the nu E is mostly emitted as a nu 3. And then what you see at the Earth is essentially 2% of the original nu E flux. However, let's imagine the scenario where the nu 3 decays to a nu 1 en route to the Earth. And then what you see at the Earth is essentially UE1 squared times nu 3, because now whatever arrives at the Earth is essentially nu 1. And then you end up seeing 70% of the original flux, and you see a huge enhancement in the flux. A similar argument can be used for the inverted mass ordering to show that you would see a suppression. So for example, in the inverted mass ordering, the nu 2 is the heaviest state. So you end up seeing like 30% or 20% of the original flux. However, if it decays to the lightest particle, which is nu 3, you would end up seeing only 2%. So you see a huge suppression of the flux. So you can do two things. One, depending on what you see, you can use this to actually put constraints on the lifetime of the heaviest neutrino. So if the supernova, for example, takes place at a distance of 10 kiloparsec, you can constrain the lifetime of neutrinos to be around 10 to the 5 seconds per EV or so, with a precision that's almost larger than 2 sigma or so. So and this can be quite large if the distance of the supernova is close by. Not only that, you can also use this to confuse the mass ordering. So for example, if you at all see a peak, you cannot really distinguish between whether the neutrino is in the normal mass ordering or with decay, or it's in the inverted mass ordering, because any kind of a decay scenario can actually change this overall picture. And this is something that can be used as a probe of non-standard neutrino decay. Not only that, depending on the decay channel, you can also basically distinguish between a decaying Dirac neutrino and a decaying Majorana neutrino. Now, this is a big question, right? The question of whether a neutrino is a Dirac or Majorana has been something that has stumped the neutrino physics community for quite some time. Now, in this scenario, for example, if the neutrino is a Dirac neutrino, you can have two, so there are always two decay channels. So there can be a channel where the helicity is conserved. So a heavy left-handed neutrino decays to a heavy left-handed neutrino under phi. Or you can have a wrong helicity channel where the helicity is flipped. So a heavy left-handed neutrino decays to a heavy right-handed neutrino and phi. Now, if neutrinos are Dirac, this heavy right-handed neutrino is essentially a sterile neutrino. So you end up losing all your flux and you don't detect them. On the other hand, if a neutrino is a Majorana neutrino, then this heavy right-handed neutrino essentially acts like the anti-neutrino, in the sense that when it interacts in the detector, it produces an E plus, which means that depending on whether you see an enhancement of events or a lack of events, you can actually distinguish between a decaying Dirac neutrino and a decaying Majorana neutrino. Not only Dirac or Majorana, neutrinos can also be something called pseudo-Dirac. So pseudo-Dirac is a scenario where there is lepton number violation, but this lepton number violation is soft. So if you look at the generic neutrino Majorana mass matrix, you operate in the limit where basically the diagonal elements are much smaller than the off-diagonal elements, which means that lepton number is violated very softly. Now, in this scenario, you can show that if you start with 3 active neutrinos and 3 sterile neutrinos and diagonalize this whole setup, you see that the sterile neutrino masses are very close to the active neutrino masses, which means that in addition to the mass square differences existing between the individual mass eigenstates, so in addition to delta m square atmospheric and solar, you would also have small splittings between the active and sterile component of each mass state. So for example, nu3 splits into a nu3 active and sterile, and similarly for nu2 and nu1. And these mass square differences are given by some quantity called delta m square, which is very, very tiny. Now you can have essentially active sterile oscillations between these two states with a baseline, within a baseline which is inversely proportional to delta m square. So if the smaller the delta m square, the longer the baselines over which these oscillations can take place. And this, of course, would be very relevant for neutrinos coming from very long distances, like a supernova or an active galactic nuclei. So in those cases, neutrinos travel over very, very long baselines, and which means that if you have active sterile oscillations over those long baselines, you would be sensitive to very, very tiny delta m square. And these oscillations would actually show up in a detector. So for example, out here I show a plot of the energy square times the differential spectra as a function of energy. So this is roughly what a detector would see. So energy square gives you a parameterization of the cross section, and this green line shows you what you would see in the standard case. But if you have oscillations from a pseudo-Dirac hypothesis, then you would see these large scale fluctuations in the spectra, and this can be used to put strong constraints on the value of delta m square that you can get. Now, this is an analysis that we also did for the Supernova 1987A data. Using these 30 events, you can actually say whether you can rule out a certain value of delta m square or not. And what we find is that just using these 30 events, one can rule out a delta m square as tiny as 10 to the minus 20 electron volt square with a reasonably large delta chi square. So for example, if you take the combination of the 3 experiments, this value can be ruled out with a delta chi square greater than 10 or so. Not only that, very interestingly, we also find that just with these 30 events, you also get a slight preference over the unoscillated scenario, which is out here, by a delta chi square, which is very marginal, like 3 or so. This, of course, not statistically significant, but this essentially stems from the fact that the neutrinos observed by Kamiokande and IMB have some contradictions, as in IMB prefers higher energy neutrinos, Kamiokande prefers low energy, and this can be explained by the hypothesis that neutrinos oscillate as pseudo-Dirac neutrinos. One can also ask the question as to whether upcoming neutrino experiments like Hyper-K and Dune can confirm or rule out this scenario. And what we found was that Hyper-K and Dune can basically be sensitive to delta m square as small as 10 to the minus 21 eV square as well for a next galactic supernova. So this would be like a prime scenario to test whether the pseudo-Dirac hypothesis exists or not. One can use this to put constraints on this entire neutrino mass square difference landscape. So what I show out here on the y-axis, you get the neutrino energy in MeV, and the x-axis is the different baselines of the neutrino oscillation experiments. And these contours are the different delta m squares that the different oscillation experiments can test. So for example, reactor neutrino experiments stay here, accelerator experiments stay here, atmospheric experiments stay here, because they essentially probe the delta m square solar and delta m square atmospheric. On this contour, you can also say that even supernova 1987A can test points out here, or one can use even high energy neutrinos to test points out here. So this entire landscape is wide open, and one can actually use different neutrinos to test different parts of this landscape. Now let's change gears a little bit and let's talk about the supernova cooling constraints. Now this idea is something that I discussed very briefly. The idea is very simple, that we have seen neutrinos emitted over a period of 10 seconds or so from supernova 1987A. So if you have new modes of any new weakly coupled particles, they would essentially act like an extra sink, drain away energy from this from the supernova engine, and then which means that the amount of energy available to neutrinos would be reduced, and the neutrino burst duration would be reduced from 10 seconds. Using this, a constraint was put in these papers that if the luminosity of the new particle exceeds the luminosity of around 10 to the 52 ergs per second or so, then the duration of the neutrino burst is reduced from 10 seconds. And one can use this criteria to put constraints on new particles, weakly coupled particles. However, it has a window of applicability. So if the particle is very weakly coupled, then it's not efficiently produced. So you cannot really produce it like that, in enough quantities. Or if the particle is very strongly coupled, then you essentially end up trapping the particle. So it's only within a certain window that you would be susceptible to this kind of luminosity emission. And this can, in principle, be used to constrain different kinds of particles like axions, dark photons, and so on. I'll be quickly talking about something called sterile neutrinos, which are very nice dark matter candidates, keV mass sterile neutrinos. And these can be produced in the core of a supernova through different mechanisms. And once you produce them, these can basically free stream from the supernova core and cool the supernova. And this had been used to put constraints on the mass in the mixing parameter space, which is given by this red contours out here. However, it was shown that because you produce these sterile neutrinos from the active neutrinos, it actually affects the potential, which means this changes the neutrino propagation. And this can, in principle, lead to some sort of a feedback effect, which essentially reduces these bounds. So the bounds that exist in absence of a feedback actually goes to this case where it actually gets reduced drastically. In principle, what we can show is that if you introduce new interactions in the active sector of this form, then you can again produce these sterile neutrinos in very large quantities. And this, in principle, can again put some constraints on the parameter space. So again, without going into the details, the idea is that any kind of new particles that you produce would basically end up cooling the supernova very fast. And then you can use this to put constraints on the parameter space. Now, of course, a galactic core collapse supernova is very rare. The rate is less than like 1 per century or so on. Now, one can basically go over to the diffuse supernova neutrino background, which is basically a sea of neutrinos from all possible core collapse supernova in the universe. And then one can use this to test new physics, because the detection of these diffuse supernova neutrinos are just around the corner. With super Kamiokande doped with gadolinium, we expect the detection to be just there. And then one can use this to test different kinds of hypotheses. Now, since I'm already out of time, I would quickly come to the conclusion. So what I tried to convince you through this talk is that a core collapse supernova loses almost all of its energy through neutrinos. This is one of the very few laboratories where neutrinos self-interactions are relevant, and this affects neutrino flavor propagation. The physics of collective neutrino oscillations, which affects this flavor propagation, is not completely understood. And this is a very hot ongoing topic of research in this field. Of course, once one detects neutrinos from a core collapse supernova, one can use this to test different kinds of new physics, such as neutrino decays, the nature of neutrinos, non-standard interactions, presence of new particles, and so on. This shows that supernova can really be one of the best laboratories for tests of the beyond standard model physics. Not only that, we also have something called the diffuse supernova neutrino background, which is essentially a collection of neutrinos from all possible supernova happening in the universe. And the detection of this is around the corner. So once we detect that, this would be a new milestone in multi-messenger physics. And yeah, with this, I will conclude, and I would be very happy to discuss more about this and take any questions in the discussion session. Thank you so much.